Hi guys, today we're going to look at integrating more exponential functions, and there will be some in here that start out as exponentials, but we don't actually have to use our exponential rules, so we'll just see how that goes. I have 4 or 5 examples for you, I think, and then tomorrow I have 3 problems for you to try, and that will wrap up the week. Next week, I think we'll spend a little more time on exponentials and logs, and then we'll move on into finding the area between two curves and wrap that up in the next couple weeks. Okay, so let's go ahead and get started. Okay. Whoops. Kind of changed my setup, and it looks like I didn't do a very good job of moving things out of the way. Apologize for that. I do have highlighters today, though. Okay, so let's look at the first example is we have e to the 2x over 1 plus e to the 2x, okay, dx. So here we have an exponential on top and an exponential on the bottom. And so we do want to usually take care of the bottom first and make that our u. And then even more important is that our e does involve that u as well, or the u involves the e. So here let's say u equals 1 plus e to the 2x. Okay, and now we take the derivative, and the derivative of an exponential is just the same thing. And then if we have a function up in the exponent, we have to take the derivative of that. So the derivative of 2x is 2. So right now we have du is equal to 2e to the 2x dx. And then if we look at the 1, remember the derivative of 1 is 0. And so our derivative right now is just 2e to the 2x dx. Okay. Now if we look at our original integral, we just want e to the 2x dx. Okay. And so if we look here, we have an extra 2. So how do we take care of that 2? Right, we just divide by 2. So we have 1/2 du is equal to e to the 2x dx. Okay. So now we can go rewrite our integral. And the top is taking care of du over 2. So I'll have 1/2 on the outside, and then du on top. And then that 1 plus e to the 2x, we let that equal u. Okay. So now we have du, or the derivative of u, over u. And if you'll recall, this is the pattern of a natural log. Okay. And so we actually get 1/2 times the natural log of u plus c. Okay. And then all we have to do is replace our u. And in this case, that's the 1 plus e to the 2x. And so that would be our final answer. So yes, we had exponentials involved, but we didn't end up with exponentials in our integral, or we didn't use the exponential rule when we did the integral. Okay, so it again all depends on how it can be rewritten. Okay, so that's example 1. Let's go to another one. We have e to the x minus e to the negative x, okay, on top. And then we have e to the x plus e to the negative x on the bottom. So the numerator and the denominator just differ by a sign. Okay. So we're going to approach this the same way. We're going to let our bottom be u, okay, because we are hoping that the top is just the derivative. Okay, so that's what we hope with u's. Okay, so if u equals e to the x plus e to the negative x, we now need to take the derivative of that. So the derivative of e to the x is just e to the x. Okay. The derivative of e to the negative x is, again, you just take the original function. Okay. But if it has something besides x up here, you have to use the chain rule, which just says go ahead and multiply by the derivative of negative x. So the derivative of negative x is a negative 1. Okay, so it becomes e to the x minus e to the negative x dx. Okay. Now, if we compare to our original, this is great news because we wanted e to the x minus e to the negative x dx. Okay, and we don't have to do any modification here because that's exactly what shows up in our original integral. Okay, so we're going to replace the top with du, and we're going to replace the bottom with u. So again, we get to use that natural log function since we have the derivative over the function. And we have nothing in front this time, so it's just the natural log of e to the x plus e to the negative x plus c. Okay. And I apologize, I just skipped ahead. And that should be natural log of u plus c, and then we plug in for u. Okay. So there is example 2. Now, is there another way to write that? Possibly. Okay, but for now, that's perfectly fine to write it. Okay. So the third example I have for you is if we have 5 minus e to the x over e to the 2x dx. Now this one has me a little worried if I'm looking at it because I don't see like anything that's related to the e on top. Like there's not another e to the 2x or anything like that. So I am going to rewrite this. I'm going to split up my function. Okay. So this is also known as 5 over e to the 2x dx minus the integral of e to the x over e to the 2x dx. Okay. And that looks like something that might be a little easier to work with. I'm even going to go one more step and simplify. Okay, so 5 over e to the 2x. Since there's only an e in the bottom, let's go ahead and move it up to the top so that all we have to deal with is an exponential function. So I'm actually going to pull the 5 out to the side. And then if e comes out or up top, that changes your exponent to a negative. So I just have e to the negative 2x dx. Okay, so that's that first one here rewritten. I pulled the 5 out to the front because it's a constant, and I moved the e to the 2x up to the top, which just changed the sign of the exponent. Okay, minus. Now here I have bases that are the same, so what do we do with our exponents when the bases are the same? We subtract them. And so we have x minus 2x. So this actually just becomes e to the negative x dx. Okay, so in actuality, this isn't that bad now. Okay, so let's just go here a minute and look at these separately. So here, if I let u equal negative 2x, okay, because we don't have a denominator now, this is just back to our integrating of basic exponentials where we let u equal the exponent. So u equals negative 2x, du equals negative 2 dx. Okay, and so really I just need to take care of dx. So I'm going to have to divide by negative 2 here. So this becomes a negative 1/2 du is equal to dx. Okay. So if I go back up here, now I have a negative 5/2, right? Because I already had that 5, and now I had to take care of that negative 1/2. So I have negative 5/2 e to the u du. Okay. And with e to the u du, that just becomes negative 5/2 e to the u. Okay. where'd it go? E to the u, right? And we'll come back and fix that in just a second because we have some things to add. Okay, now same thing up here, except we want to let u equal negative x this time. And so that means our derivative is negative 1 dx. Okay. And so we want dx to be by itself, so we get a negative du. Okay. And just checking I have my signs right, sorry. So we get negative du equals dx. Okay. So here we end up with, so we have a minus a e to the u, du in this case, okay? And we need a negative out here, but it was already a negative here, so that turns into a plus. And so, what do we end up with here? So we get negative 5 e to the u plus e to the u plus c. And if we go plug in our different u's, okay, these are different u's, we can't combine them, okay? So this is negative 5 halves e to the negative 2x plus e to the negative x plus c. So this one we had to break it down and go from there. Okay. Let's see. So let me know if you have questions on that one. Okay. And then a couple more. So this one's going to look pretty scary to start with, but it's really not that bad. We have e to the 2x plus 2e to the x plus 1 all over e to the x dx. Okay. So again, my worry here is we do try to let u equal the bottom and then the derivative be the top, but there's no way that the top is the derivative of the bottom in this case. Okay, so natural log's probably not going to work here. So another thing I can do is just split it up like I did in that previous problem and see if anything nicer comes out of that. So we get e to the 2x over e to the x plus 2e to the x over e to the x plus 1 over e to the x dx. Okay. So, and you could go ahead and split them up in their integrals now or simplify, whatever works for you. And I probably don't do it the same way each time. So e to the 2x over x. Again, we have the same basis, so we subtract our exponents. So I get e to the x, and I'm going to go ahead and split it up at this point. So I get e to the x dx, okay? And then here I have 2e to the x over e to the x. So the e to the x's cancel out or divide out, so I end up with plus 2. Okay, so the integral of 2 dx. And then finally I have 1 over e to the x. And since there's nothing else involved with it, we just want to bring that e to the x up to the top. And when we do that, that changes into a negative x. So we get e to the negative x dx. Okay. And so now all we have to do is integrate these, and it actually becomes a really easy problem if you think about it compared to some that we've done. Okay. So the integral of e to the x dx is just e to the x. Okay, that's what we like about e to the x. It's the integral of itself. Okay. Now, what about 2? Well, when we have a constant, we just you just add an x on, so we get 2x. Okay, and then e to the negative x, if you recall from our previous problem, it just becomes e to the negative x, but then you have to take the derivative of it, so it becomes a negative. Okay, and so we've integrated all three of those, and then we just tag on c since it's an indefinite integral. And we are through with that. Okay. So sometimes the most complicated looking ones just need to be rewritten, and then they turn out to not be that bad. Okay. And then finally, let's look at the trig one. Okay. And so we have e to the tangent of 2x, okay, secant squared of 2x dx. Okay, so yes, I know this one looks ugly. We have e's as well as trig. Okay, there's one comfort in the sense that tangent and secant are both of 2x, and so that's going to be hopefully good news for us. Okay, since we're dealing with exponentials and we don't have a denominator, we do want to go let u equal our exponent of the e. Okay, so let's let u equal tangent of 2x. Now all we have to do is take the derivative of tangent of 2x, which I know you probably don't know off the top of your head. I don't, so you either need your chart or go back where we had notes that had it in there. Okay, you can also Google online the integral of these or the derivative of these, but the derivative of tangent is secant squared, okay, of u, right, of the inside function, times the derivative of the inside function. So we would need a 2 here. So du equals 2 secant squared 2x dx. And then if we go look at our original problem, we just want secant squared 2x dx. Okay, so what does that mean we have to do to manipulate it to look like we want it to look? Well, we've got to get rid of that 2, so we just get 1/2 du. It's equal to secant squared 2x dx. Okay, and so I can now rewrite this as e to the u du. Sorry, but we need that 1/2 out there. Okay, and so then this is a problem we know how to take care of. This is just 1/2 e to the u plus c. So we get 1/2 e to the tangent of 2x plus c. And we are through with that. Okay, so the big thing to remember is the derivative of e to the x is e to the x, so is the integral of e to the x. The integral of e to the u is just e to the u. Okay, but you may have to do some reworking in there to make du work. And if we have du over u, we want to use that natural log function. Okay, so those are the notes for today. If you have any questions as you went through the notes, please let me know. I will try to answer those as best as I can. And tomorrow, like I said, you'll have 3 problems to work on. So have a great day.